Okay, let's learn about geometric. So this is the last lesson of Unit 4. This is Part F, Part 3. So Unit 4, F, Part 3. This is the homework. The geometric setting arises when we perform independent trials of the same random process and record the trials to get one success. That's key. Each trial, the probability of success must be the same. Really very similar conditions to geometric. But the condition about set number of trials, not the case here. I would summarize geometric as when it said getting one success. I like using the word you get your first success. Like I want to get my first heads on my fifth flip. I want to get my first hit on my seventh at bat. I want to get my first make of my free throw on my third shot. So you're trying to get the first success. Usually not on the first try. Usually it's, second, third, fourth, fifth, or something like that. So roll a pair until you get doubles. You're going to keep going. You're going to fail, 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 fail until you get doubles. Basketball, keep attempting three-point shots. Miss, 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 miss until you finally make it. Keep trying to guess a random integer 1 to 10 until you get it right. These are geometric settings. Notice there's not a set number of shots. We don't know what the set number of shots is. But you're trying to get the first success at some point in time. This is just telling you what a geometric random variable is. Pretty similar to binomial, but no set number of trials. This is the formula. So this is actually helpful. This is the formula for, and so that first parentheses there is the probability of failure. You want to fail however many times. You want to fail x minus 1 times, and then have your first success on the x time. That is on your formula sheet. Your teacher's planning to give you 10 homework problems, but you can have a chance to play the lucky day game. A student will be selected at random from your class, asked to pick a day of the week, like Thursday. Teacher will use technology to randomly choose a day a week as the lucky day. If your student picks the correct day, I guess out of 7, class will only have 1 homework problem. If the student picks the wrong day, your teacher will once again select a student at random from the class. This chosen student will pick a day of the week, and your teacher will use technology to choose a lucky day. If the student gets it right, the student will have 2 homework problems. Oh, wow, it's an interesting game. So they keep doing this. Assign a number that is equal to the total number of picks by member of your class. After a quick discussion, the class decides not to play the lucky game because they don't want to risk getting more than 10 homework problems. Did the class make a good decision? Find the probability that the class receives exactly 10 homework problems as a result of playing this game. So X is the chance of having your first success, successfully picking the day of the week correctly on the 10th try. Well, I guess X is the number of homework problems. It's a random variable, so we'll find out what that is. The chance of success is 1/7, that's for sure. We want to find the probability that X is equal to 10, so that's where you put in the 10 there. We'd like that to happen. Perform your calculation. So I'm going to show you 2 different ways of doing this. One is like old school, you don't really need a formula. You've got 10 kind of slots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you're going to multiply all those together. You want all of these guys to be fails. You don't want, and then you want this one to be success on the 10th try. So without using the formula, what's the probability of failing each time? So you're going to multiply all these numbers, by the way. So failing would be 6/7. Most of the time you're going to fail. 6/7, 6/7. I'm writing 6/7 over and over and over again. times. So all those would be multiplied. And then the chance of success is 1/7. So you'd multiply all those. Now the formula makes it a lot easier. Remember, so x is equal to 10 in the problem. We're trying to get 10, the first success on the 10th try. And then probability of success is 1/7. So if I plug into the formula, this would be 1 minus 1/7 to the power of 10 minus 1 times p, which is 1/7. That looks a lot like 6/7. That looks a lot like 9 times with it. We did that. Yeah, that's the same formula, right? So you can think of it different ways. Some people don't use a formula. They just kind of do slot method and fill in the blanks there, which would be fine. You can also just use the formula. So what was the answer there? 3.57% of the time. Okay, that's not very often that would occur, but I guess we don't know how many times it'd be greater than that or less than that. Maybe we should find this. So this is kind of a range of things. So describe the probability in words. We want to find the probability that x is less than 10, so that we have our first lucky day win before 10. So 9, be happy to 8. You'd have to do this a bunch of times. To do this by hand, I mean, because you're saying that x needs to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So you'd have to do geometric 9 times and add them all up. So that first time is just 1/7, because your first time you would get lucky and like that would be 0. That would be the first guess. The second one would be on your second time. So, and you can't get on your 0 time really, but 6/7 times 1/7, and then the next one, and you keep adding those up. Man, that'd be a lot of work to do that, but you could get that eventually. Oh, I didn't show you the shortcut, did I? Let's go back to this one. So let's see what we get when we do this in the calculator. So there is a way, there's a shortcut way. So menu 5, it's under distributions, I'm pretty sure. If you scroll up, you'll see geometric PDF. So this one, the first example there was getting exactly 10, right? So probably success is 1/7. 10 is the x value, 0.035. So it does it for you. For the next example, menu 5, geometric CDF. So we really want a lower bound of 0, an upper bound of 9. Oh wait, probability of success is 1/7. Lower bound of 0, upper bound of 9, and we get the answer to the second one. I'm just curious. Just want to make sure I was thinking the right way. If this is 1, yeah, it didn't change. 0 is impossible, right? You can't get the first miss, or the first make, I guess, first time you kind of win the game on the 0 try. I would just make sure that didn't make a difference. And so they did it the long way. They did all that. They got 0.7503. We did it the shortcut way, got that. There's a 75% chance the class will get fewer than 10. So if they play the game, yeah, it's pretty good likelihood they're going to get less than 10, but they do have the possibility of getting more than 10 homework problems. So there is that. We just did that on our calculator. Okay, these are the formulas for mean and standard deviation of geometric variables, geometric random variables. So 1 over p might be somewhat intuitive. Standard deviation certainly is not intuitive. Those are on the formula sheet for sure. Remember the draw a 3, get it free. The x is the number it takes to get the first free order. The fact is it says first free, so we don't know if that's going to be the second customer, the third customer, the fourth customer, etc. We just don't know when the first free order is going to be given. So you want to use your mean formula here. So the mean would be 1 over p. So 1 over 1/7, which would be 7, right? Oh, sorry. I'm thinking about the wrong problem. I'm thinking about the 1/7, the playing the other game. The mean would be 7. This one, the chance of getting an ace is 4 out of 52, or 1/13. So if you do 1 divided by 1/13, that's the same thing as 13. The average number a customer takes to get the first free order would be about 13. The average would be 13 if they ran this promotion many times. What's standard deviation? Just plug into the formula. There it is. So 1 minus 1/13 over 1/13 is 12.49 when you have the square root of that top part. If you did this on many, many days, the number of customers takes their first free order would typically vary from the mean by about 12.5. Okay, that's the lesson for today. In the game of Chuck-a-Luck, a player places an integer, a bet on an integer from 1 to 6. We've seen that. One determined player decides to play as many games as it takes to get a win. Okay, probability of winning a single game is 0.421. Find the probability the player must play 4 games to achieve a win. So that x equals 4. So we're going to use the formula, plug into the formula, right? So the formula was 1 minus p, so 1 minus 0.421 is 0.579, to the power of 4 minus 1, which is 3, times p, which is 0.421. Part B, probability that x is greater than 4. I would definitely use CDF. This is a range of values for x. We want it to be 5. Ooh, this is interesting, though. So greater than 4. Ooh. Yeah, because we don't know how big to go. I mean, 900, 9,000, 90,000. So you could do 1 minus the probability of x is smaller than or equal to 4. So if you want greater than 4, we could do smaller than or equal to. So to do that for part B, let's see if we can do this. So we will go to CDF, geometric CDF. Probability of success is 0.421. Lower bound is 0. Upper bound is 4 because we want greater than 4, so 4. So we'll get this answer, and we do 1 minus that answer. Should be 0.1123. Yeah, 0.112. There's about 11.2% chance the player would need more than 4 games to win a game of Chuck-a-Luck. Roll 2 fair dice at as many times as needed to get doubles. Let x equal the number of rolls it takes. Note the probability of getting doubles in any roll is 1 out of 4. Is that true? That seems awfully high. So, I would have thought it's less than that, but we're going to go with it. Calculate, interpret the mean. So we're going to use 1 over p is the mean. So that would be 1 over 1/4 or 4. You take 4 rolls. I almost want to do some testing on that one. I don't know. Something seems funny. Calculate, interpret the standard deviation. Again, this is just plug into the formula. So 1 minus p is square rooted up top divided by p is 3.464 rolls. The rolls number it takes to get doubles would typically vary from the mean by about 3.464 rolls if you play rolled and play this game many times.